Okay. Okay, so if we have this differential system, this system of differential equations, again we have x and y as our variables, but they're actually functions, and we have derivatives of x and y. These are first order. They don't have to be first order, because all we have to do to solve this equation is Laplace transform them, and it becomes just a simple enough algebra problem with two variables. The variables are going to be your two Laplace transforms, your Laplace transform of x, your Laplace transform of y. You solve for those Laplace transforms and then just inverse transform them in the way that we're used to doing. So there's not a whole lot that's new here. But let's just see how it works out. Okay, so this tells us I'm just thinking about notation. I almost wish I'd have used x prime here, but anyhow, the Laplace transform of dx dt equals the negative of the Laplace transform of x plus the Laplace transform of y. Okay, well, that's your first equation. It's transformed. Well, I'll complete the transform in a minute. And we have some initial conditions, but we'll worry about that in a second. Okay, then we have the Laplace transform of dy dt equals 2 times the Laplace transform of x. All right, I think I've done everything correctly. Well, this becomes s times the Laplace transform of x minus x of 0. See, I almost wrote y. Got to watch me. Negative L of x plus L of y. Then this becomes s times the Laplace transform of y minus y of 0 equals 2 times the Laplace transform of x. Now if you think ahead a little bit, I'm going to keep it, I'm not going to put in x of 0 and y of 0 until the next step. So, it may be even not till the one after that. Because of course your initial conditions can change. Whatever the system is, its response is going to be dictated by the Laplace transforms and the initial conditions. Okay, so the system itself has a transfer function that depends on the Laplace transforms, and then specific behaviors that depend on your initial conditions. Okay, I'm running out of room. I don't think I'm going to need all that much room, so I'm going to risk it and move over here. If I rearrange the first equation, I get s times, I don't want to do that, I want to factor out the L. Okay, I'm going to get an SL of x plus an L of x when this comes over here. So I'm going to get s plus 1 times Laplace transform of x, and your book does use a capital X instead of a Laplace transform of x. I stick with this because it gets hard to distinguish the capital X from the lower x, and I like making these fancy L's anyway. Okay, we get this, and then it's going to be plus L of y. And we can see down here that L of y is going to be easy to solve for L of x. Okay? So when we solve for L of y here, we're going to be plugging that back in here. We're going to have an expression involving L of x, which will combine with this, and we'll factor out the L of x from everything we get, and it's going to work out rather nicely. Okay, and then this is going to equal x of 0. Down here, we get s minus 2 L of y. Okay, bring the 2 over here, equals y of 0. Okay, well then, L of y equals y of 0 over s minus 2. And that implies then that s plus 1 L of x plus y of 0 over s minus 2 left something out. And actually what I did here was, yeah. Okay, let's fix it. This is wrong. And everything that follows here comes from that, so it's wrong. I did this as this was an L of y. And then I got a couple of steps down and realized that I didn't have anything to substitute in here for L of y that involved L of x. If this is an L of y, we could solve this one independently anyway. Okay, so second equation should have been SL of y equals y of 0 plus 2L of x. So now when we solve this for y, we get L of y equals, and I'll do it in two terms because that's the way it's going to come out here, y of 0 over s plus 2L of x over s. And now when we substitute into the first equation for L of y, we're going to get s plus 1 L of x plus y of 0 over s plus 2 times the transform of x over s, and that's equal to x of 0. Well, now we're going to put our y of 0 over s on the other side, get rid of it for the moment. And then we're going to combine this 2L of x over s with this, and we're going to get s plus 1 plus 2 over s L of x equal to this. Then we probably put this over the common denominator, and I'm actually going to do the step. It should be unnecessary. So we're going to have s squared plus s plus 2 over s L of x equals, write it out, x of 0 plus y of 0 over s. So that now we got our L of x. So that's going to be divided by s squared plus s plus 2, but also multiplied by s. So, and we're going to multiply by s over s squared plus s plus 2, and you know, this 2 that I wrote here looks a whole lot like an s. once you get to writing s's, you keep it up and you make an s out of yourself. Okay, s squared plus s plus 2. So we got our s over s squared plus s plus 2 multiplied by this. Conveniently, that gets rid of the s here, so we don't have to mess with this. So this equals then s x of 0 plus y of 0 over s squared plus s plus 2. And you know, I really don't want a plus 2, I want a minus 2 there. Doesn't look like I'm going to get one though. I really want one because then I can factor this. Makes it easier to do the partial fractions. If we don't do that, and I think we're going to not be able to do that, we're going to have to complete the square in this thing, and I'm not sure I've done that, so if I complete the square on that, I'm going to get like an s, I'm going to get like a 1/4, and we're going to get fractions, and this is a text problem, so you probably don't have fractions. So somehow I've probably managed to mess something up. I don't see it. Well, anyhow, perfectly good inverse transform, or perfectly good transform over here. We've got to inverse transform it. And the way we do that depends on what x of 0 and y of 0 are. But you see from this example that we get something that we can work with. So we can figure out what our x function is just by inverse transforming whatever we have here. And then, of course, since we know L of x, we can put that in here. And we also then have our Laplace transform of y. So that now s times the Laplace transform of y is going to equal y of 0 plus L of x So I'm going to have to come back here to write this. We're going to put two underlines here to indicate that this step doesn't follow from this, it follows from this, which is all the way over here. It follows that the Laplace transform of y is y of 0 over s plus s x of 0 plus y of 0 over s squared plus s plus 2. Now once more I swear that this thing has to be a negative 2, and I'm still not seeing how it comes out to be that. I'm going to check the solution. Now before I look, if the solution, well, the solution is going to involve sines and cosines. If it involves sines and cosines of fractional multiples of t, then it's going to be because of this. We're going to see. I don't think it does. I think it's going to involve 2t and negative t. Yep, that involves t and negative 2t. So my intuition is right. I screwed up somewhere, and it doesn't take much intuition to predict that. There should be a minus 2, and there might be other algebra errors in here. Also, the rest of what you get, the coefficients you get and so forth, depend on what x of 0 and y of 0 are. So you got to plug in your values of x of 0 and y of 0 in order to get your specific functions. But that's the process, and it's not a difficult process. Okay, you simply do the Laplace transform, you try to get the algebra right, and you solve for L of y in terms of L of x, plug into the first equation. Yeah, I still don't see the error. And then you just do the algebra and you do your inverse transforms and you get your y and your x functions and you're done. It's pretty slick. There are other techniques we can use with linear differential equations, and I actually hope to at least show you those. I'm debating right now what we're going to do between now and the end of the semester. Because we're about to wrap up the chapter on Laplace transforms. I was planning to go back and get some of the later sections of chapter 4 that we postponed. I'm weighing that against just leveraging what you know about linear algebra and eigenvalue equations, which should give you no trouble, to at least get the very basics of solving systems of linear differential equations. Now, one big thing here, and I'll do an example in a minute, that involves second derivatives. Okay, and you see if you've got second derivatives, you're just going to get some s squareds over here when you do the Laplace transforms, and that's not going to be any big deal. And if you get second derivatives here and second derivatives here, maybe you're going to get an s to the fourth. Just makes your expression a little harder to factor. Inverse Laplace transform, just a little more work on the partial fractions, but it's not really a big deal conceptually, just a little more work. Okay, well, we're going to see an example. That's what we're going to do next.